So I made the daily mistake of eating a good amount of spaghetti before this. I'm like extra sleepy. I got the itis. So my energy is super duper low, but we're gonna work with it. Let's see. Let me share my screen. Like this. I think that looks good. And we're gonna start here. Okay, gentlemen. Let's see. So we are welcome, gentlemen. We are at what today is what? Today Monday? Yeah. The top of week 6, I think it is. So we're just going to be continuing with chapter 1, and today we're going to be working on section 1.5, transformations of functions. No real updates other than hopefully you all have found your full access to Pearson. I think they came to a conclusion last week where there is a discount available, but you have to get it through the bookstore. It's like it should be like $100 for two years of full access to Pearson. And I use basically this platform or this setup for 3 different classes at least, if not more. I use it for College Algebra 1, College Algebra 2, and pre-calculus. So it just depends on whatever the institution needs. And I think I use it whenever possible. I use Pearson whenever I can, but not all the professors use this, okay? That's the only thing. Otherwise, as long as you're making your way through the assignments in Pearson and just making sure to get into the Zoom call to get your attendance credit, then you're Gucci. So a few objectives here. 1, we like to define transformations of graphs. 2, use vertical or horizontal shifts to graph functions. 3, use reflections to graph functions. 4, use stretching or compressing to graph functions. So what do we mean by transformations? If a new function is formed by performing certain operations on a given function f, then the graph of the new function is called a transformation of the graph of f. Something like last time we reviewed or we explored a library of parent function or a library of basic functions. And so now we're going to take that collection of functions like the constant function, identity function, squaring function, which is basically a U-shaped graph, a cube function, which is like an S almost, absolute value, right? We did what we could together, and then I do expect you all to kind of watch my pre-recorded lectures. And then on Wednesday of last week, we went through as many of the corresponding homework assignments. So we'll probably do a similar structure here where, today we'll get through just about all of this section. And then on Wednesday, we'll go through as much of the homework together as we can. All right, so in this example, it says let f of x be absolute value of x, g of x be the absolute value of x plus 2, and h of x be the absolute value of x minus 3. We're actually sketch the graph of these functions on the same coordinate plane and describe how the graphs of g and h relate to the graph of f. So here, let's start by making a table and plotting some points, right? So I'll start with the horizontal bar. We have what? X, f of x, g of x, and h of x. Okay. I'm just going to choose several values of x. Let's let x be -3, -2, -1, 0, 1, 2, 3. Can anybody tell me the general shape of absolute value of x? What does that shape look like, or that graph? In general, what does it look like? Looks like a letter in the alphabet. Which letter? Right? And or what does absolute value mean? Like, for instance, if we do the absolute value of -3, what does that mean? So absolute value is the positive distances away from a number. I don't know why I can't say it. Absolute value is the positive distance away from 0 that a number is, right? So the absolute value of -3 is 3 because it's 3 units away from 0. Absolute value of -2 is 2, 1, 0, 1, 2, and 3. Okay. So then with g of x, we want to take those results and add 2 to the outside. So we want to add 2 to those results, right? So 3 plus 2 ends up being 5, 4, 3, 2. And then I think it goes back 3, 4, 5. Okay. And then H, sorry, I'm like distracted. Let me see. Where'd it go? Oh, so we're subtracting 3 from f of x. So then that's going to be what, a 0, -1, -2, -3, and then it repeats, -2, -1, 0. As always, if anything is not clear, feel free to unmute yourself or type in the chat to get my attention and we can talk about it. So let's look at the graph here. So let's introduce some graph paper. This one is good. Oh no. Paper graph. Okay. Oh, why does it keep? Oh, I know why it's going away. That's a pain. Let's try this again. So I had to at least introduce a space. It's kind of weird. Paper. Let's try it this time. Should work. All right. Like if I don't put a space in it, then it recognizes that as empty and it goes away. Okay. I don't want that. Let's go here. And then like this. Hopefully that's not too big. Come on. Like this. Copy. Okay, that looks decent. Okay. So we'll let our positive x go in this direction. And we'll let our positive y go in this direction. Okay. And this is our positive x, positive y. The x's, this needs to be what? Did we lose? We lost. Oh, there it is. Okay. Yeah. X's go from like -3 to 3. Let me see. So we can go 1, 2, 3, 4. That's decent. 1, 2, 3, 4. That's decent. The y's, we need to go, the lowest y is like -3 and that goes up to like 5. Okay. 1, 2, 3. That's enough. 1, 2, 3, 4, 5, 6. That's decent. So this is our origin. 1, 2, 3, 4, 5. 1, 2, 3, 4. 2, 3, 4, 5, and 6. And these are negatives. Okay. All right. So we're going to leave f of x in black. We'll do g of x in green. And we'll do h of x in orange. Style. Okay. All right. So then f of x. So let me see. Let's start. Well, I guess we can plot points. Let me see. I'll go here. Paste. Copy. All right. Let me see. So we have the point, what, -3, 3, which is here. Okay. -2, 2. Here. -1, 1. Here. The origin is already plotted, and then 1, 1. That's what else I can do. 2, 2. And then 3, 3. So then if we connect all these with using straight edges, absolute value, we get this kind of shape. I think I'm gonna just copy that. Paste. That looks decent. Right. So that's our graph of f of x equals absolute value of x. So then G, we're going to plot those x's versus those y's. And so I'm going to do that in the following way. Let me just get a copy of like this. Copy. I'm going to paste like here. Paste. Okay. Let me delete that. Let's try that one more again. This. Copy. There we go. That's better. Okay. Oh, and then so we're doing the G. So G is in green. Oh. Style. Style. Fill. Green. So let me see. The vertex is at 2 right here. That looks decent. And then I'm just going to readjust this a little bit. That looks proper. Okay. And then, oh, I should have copied that. I always forget. Paste. Let me see. I don't need this, that. Okay. And we'll do this in orange. Let's try it again. Okay. And the vertex for this one is at -3, right? So you can like confirm that all those points are plotted correctly, right? And you should notice something from the original graph, like from the black, as we went from the black to the green and from the black to the orange, right? So what this is, notice that with G, we added a positive on the outside of our basic function, right? So this brings us to our first two transformations, right? We added a positive on the outside of our basic function. So we went from the black to the green. So adding a positive on the outside, you should notice that it moved our graph up by 2 units. Subtracting a positive on the outside moved our graph down 3 units, right? Okay. So outside manipulations cause a vertical change and they tend to follow our intuition. Okay. So then I think we have a type version of what we just experienced. Absolute value, when we added 2 on the outside, I moved it up by 2 units. When we subtracted a positive on the outside, it moved it down that many number of units. It was 3 in this case. So let C be some positive number, then the graph of y equals f of x plus c is going to be the graph of y equals f of x shifted c units up. And the graph of y equals f of x minus c is going to be the graph of y equals f of x shifted c units down, right? So the moral of the story here, now in total, we're going to have about 10 transformations total. I think that's how many there are. So the concept behind the transformations is simple, but I would say that it's not necessarily easy because it can be information overload. All right, so this counts as the first 2 of the 10. And the takeaway from here is that when basically outside manipulations generally cause a vertical change and they follow our intuition, right? We add a number larger than we add a positive, it goes up. We subtract a positive, it goes down. All right. Okay. So then here, in this example, we're given the f of x equals x squared. You should know that shape. All right. f of x equals x squared, g of x equals x minus 2 squared, and h of x equals x plus 3 squared. So a table of values for f, g, and h is given on the next slide. The graph of the three functions f, g, and h are shown in the following slide, and describe how the graphs of g and h relate to the graph of f. I would like to do this one, but we don't need to. Okay. All right, so hopefully you're aware that like f of x equals x squared is basically a parabola, it's a U-shaped curve. So now in the previous example, we saw how outside manipulations to our function affected the graph. Now we want to see how inside functions affect the graph, right? So if outside manipulations cause a vertical change, then you can anticipate inside manipulations to do something. All right, let's look and see. So let's make a table. We'll choose several values of x, find the corresponding f, g, and h. And I think it's already been done for us, so we're going to use this. So they let x be -4 to 4. And so with g, notice that we subtracted 2 inside our basic function. So when we do inside manipulation, that affects our x values, right? Okay. So we're starting with the U-shaped curve. I feel like let's look at the graph and then we'll see how these affect, right? But notice for G, we subtracted 2 on the inside. For F, we added 3 on the inside. So if you just had to guess, if we subtract 2 on the inside, how do you think that's going to affect the graph? So take a moment to yourself, all right? If we subtract a positive 2 on the inside, how does that affect the graph? Let's see. So the blue is the original. When we subtracted 2 on the inside, notice that negative x is to the left, but this actually went to the right, all right? So intuitively, you might feel like, oh, well, it's a -2 on the inside. We should go to the negative x direction. The inside is typically the reverse of everything. Inside manipulations typically cause a horizontal change, and it's the reverse of our intuition. So if we subtract a positive on the inside, then it actually moves to the right, which is in the positive x direction. One way that I remember the inside manipulations, as far as rigid transformations, I try to think of what value of x makes the inside 0. Notice that +2 makes the inside 0. So we move this to the right by 2 units in the positive x direction. For the red, we added a positive on the inside. So keep in mind that -3 makes the inside 0 there. So then we move 3 units in the negative x direction, all right? So again, as a recap, outside manipulations typically cause a vertical change and they follow our intuition. Inside manipulations cause a horizontal change and are typically the reverse of our intuition. Okay. All right, and I think this is just a type version of what we just experienced. So then when it comes to horizontal shifts, let C be positive. Let me check this one time. Let me get the student. And my energy is shot. I am struggling. So like this, like that. Let's let them in. So for the discount, basically just contact the bookstore and just explain, what you're trying to do, because they're the ones that have that access code. You have to contact them. For the person that missed last week because of the marching band, just remind me towards the end of class so I can update my attendance. Okay, just remind me towards the end. That's fine. Okay. All right, let's keep going. All right, so in this example, we're asked to sketch the graph of the function, right? Can anybody describe to me either what's the basic function here or basic shape, and then or what's the basic function or the parent function, and then can you describe what the parent function looks like the shape of the parent function? Anybody know this one? We have this g of x. Okay. So square root function, right? So the basic function here is square root function. So the way I remember the shape, the general shape of square root, to me, it looks like the top half of a sideways parabola. So if you envision like a U-shaped curve, you turn it to the right to put it on the side, you cut it in half horizontally, you keep the top half, that's the shape of square root function. So again, the way I remember square root function is the top half of a sideways parabola. So then when we're identifying multiple transformations in one equation, the recommendation is to work our way from the inside to the out. So we start with the innermost nested transformation. We do that one first, and then we work our way out. So the innermost nested transformation in this case is going to be the +2. Because that +2 is inside our basic function, it should cause a horizontal change and be the reverse of our intuition, right? So the notes here would be the basic function we're going to work with is y equals square root of x, okay? That +2 tells us to take the square root of x and move it left 2 units. Left 2 units. And then that -3 outside of our basic function, that causes a vertical change and it follows our intuition, so that means we should go down 3 units. So all this is saying is that start with the square root function, go left 2 units, and down 3 units. And you should be good to go. Let me see it here. Let me see. So you can see the square root function at the origin, and then they go, when they say the +2 on the inside, that moves it left by 2 units, and then they go down 3 units, and the red is our final graph. Okay. So let's see, we've talked about So we talked about 4 different rigid transformations, 2 on the outside and 2 on the inside. If we add a positive on the outside, that should go up that many number of units. If we subtract a positive on the outside, that should go down that many number of units. If we add a positive on the inside, it should go to the left that many number of units. If we subtract the positive on the inside, it should go to the right. Okay. Outside is vertical, inside is horizontal, and is the reverse of our intuition. Okay, so then the graph of y equals negative times f of x is a reflection of the graph of y equals f of x in the x-axis. If a point x comma y is on the graph of y equals f of x, then the point x comma negative y is on the graph of y equals negative f of x, right? So notice that negative is outside of our basic function. So when we, again, outside manipulations typically cause a vertical change. It's going to cause a vertical change. And so if we multiply the outside by a negative, that's like our y values are going from positive y to negative y. So essentially, multiplying the outside of our basic function by negative causes our graph to flip vertically over the x-axis. So it's like our y values, the x values stay the same, but our y values go from positive y to negative y. Okay, so it flips vertically over the x-axis. And here's an image kind of displaying that. So if the blue is our original function, if we multiply the outside by a negative, the x values stay the same, but the y goes from positive y to negative y. So it flips vertically over the x-axis. Okay, so multiplying the outside by a negative causes it to flip vertically over the x-axis. So then what do you think happens when we multiply the inside by a negative? Right? If multiplying the outside by a negative causes it to flip vertically, then multiplying the inside by a negative should cause it to flip horizontally over the y, right? In that instance, the y values stay the same, but the x's go from positive x to negative x. So it's going to cause a flip horizontally over the y-axis. So the graph of y equals f of negative x is a reflection of the graph of y equals f of x in the y-axis. If a point x comma y is on the graph of y equals f of x, then the point negative x comma y is on the graph of y equals f of negative x, right? So that gives us 2 more transformations. The first 2 were outside manipulations causing a vertical shift. Then next we had 2 inside manipulations causing a horizontal shift. This next set of 2 is multiplying by a negative and it's causing a a reflection about an axis. Outside manipulations cause vertical changes. Inside manipulations cause horizontal changes. Okay, so here's an example where if we multiply the inside by a negative, it flips horizontally over the y-axis. Again, our y values stay the same, but the x's go from positive x to negative x. Okay, so explain how this graph can be obtained from the graph of y equals absolute value of x. So we should be comfortable with this basic shape by now, absolute value of x, right? That was like, we had that one a moment ago. That basic shape is going to be a v. And so since we have multiple transformations in one equation, to list as we go to apply our transformations, the recommendation is, again, work our way from the inside to the out. All right. So we're starting with the basic function y equals the absolute value of x. It's a V-shaped graph. The innermost nested transformation is going to be the -2. So we subtracted 2 on the inside. So that should move it into the positive x direction. So we should go to we start with a V. We shift it to the right by 2 units. So the first transformation is we're going to go right 2 units. Okay. So then working our way out, the next manipulation is we multiplied the outside by a negative. Right. So multiplying the outside by a negative is going to cause a vertical change. So it should flip vertically over the x-axis. So we're going to flip over x-axis. Okay. And then the last transformation is that +3 on the outside of our basic function. That's going to cause a vertical change. It follows our intuition, so it should go up 3 units. All right. So these are our transformations. We're starting with a V-shaped graph. Says to go right 2 units, flip vertically over the x-axis, and then go up 3 units. So we can see that here. We started with the V-shaped graph. When we introduced the -2, it shifted it to the right by 2 units. When we multiplied the outside by a negative, it flipped it vertically over the x-axis. And then when we added the 3 on the outside, it shifted it up 3 units. Okay. We actually are getting through this a little bit quick. Okay. So then let f of x be the absolute value of x, g of x be 2 times the absolute value of x, and h of x be 1/2 times the absolute value of x. We're asked to sketch the graphs of f, g, and h on the same coordinate plane and describe how the graphs of g and h are related to the graph of f. Okay. So we chose several values of x. We're going to find the corresponding f, g, and h. So when x is -2, absolute value of -2 is what? 2. And then 1, 0, 1, 2. Okay. So then g, we want to take those results and multiply them all by 2. So then we get 4, 2, 0, 2, 4. And then for h, we want to take the results from f and multiply each of those results by 1/2. So we get 1, 1/2, 0, 1/2. Okay. So what we're doing here, we're seeing what happens when we multiply a basic function on the outside by a couple of different numbers. The distinction between these numbers is in G, we're multiplying the outside by a number larger than 1. And with H, we're multiplying the outside by a number between 0 and 1. Okay. So, the answer is kind of on the screen, but so let's see what happens if we were to plot these on the same coordinate plane. We have that here. So then our f of x equals the absolute value of x. Notice it's a V-shaped curve, V-shaped, the V-shaped graph. So then for G, we multiply the outside by a number larger than 1, right? So to go from the blue to the red, we call that a vertical stretch. I'm not sure if you all are aware of like taffy, the old candy is, but like imagine this image was drawn on taffy, and we took that taffy and stretched it vertically. It would get more tall and skinny, right? So multiplying the outside of our basic function we call that a vertical stretch by a factor of 2. The x values stay the same, but the y values in that case, get multiplied by 2. For the green, to go from blue to green, it's like our y values were cut in half. The x values stayed the same, but all the y values got cut in half. So we call that a vertical compression, or vertical shrink. So if it was drawn on Laffy Taffy and we smushed it vertically, it would get short and wide, right? Okay. So the moral of the story is, in this instance, multiplying the outside, let's see it here. Yes. Multiplying the outside of our basic function by a number larger than 1 is going to cause a vertical change, and it's going to follow our intuition. So it's going to get, as we call that, a vertical stretch. It's going to get tall and skinny. It's going to get bigger vertically. Multiplying the outside by a number between 0 and 1, that's called a vertical compression or vertical shrink. So the image should get short and wide, right? So the graph of y equals a times f of x is obtained from the graph of y equals f of x by multiplying the y coordinate of each point on the graph by a and leaving the x coordinate unchanged. The result is it's going to be a vertical stretch that moves away from the x-axis if that a is larger than 1. It's going to be a vertical compression towards the x-axis if that a is between 0 and 1. If a is negative, first graph the absolute value of a times f of x by stretching or compressing, and then flip the result vertically. Then basically flip it over the x-axis. That's if that's if a were negative, right? So basically, we would use this notion for multiplying, doing vertical stretching or compressing, and then apply reflecting, like what we talked about in the previous example. Okay. So then we saw what happens when we multiply the outside of our function by different types of numbers. So now we want to see what happens when we multiply the inside of our basic function by different types of numbers, right? So again, remember, inside manipulations typically cause a horizontal change and are typically the reverse of our intuition, okay? So if you had to think intuitively, if we multiplied the inside of our function by a number between 0 and 1, intuitively, you might feel like, oh, okay, well, it's inside, so it should be a horizontal change. And because it's between 0 and 1, then maybe it will cause a horizontal shrink by that factor, right? But in reality, it's the reverse. It does cause a horizontal change, but if we're multiplying the inside by the number between 0 and 1, it actually causes a horizontal stretch, right? So it gets wider. It stretches horizontally away from the y-axis, right? So, and then if we multiply the inside by a number larger than 1, it's going to cause a horizontal shrink, right? Yeah, let's just go with that. So the graph equals y. The graph of y equals f of b times x is obtained from the graph of y equals f of x by multiplying the x coordinate of each point on the graph by 1 over b and leaving the y coordinate unchanged. So the result is, we say it's a horizontal stretch away from the y-axis if that b is between 0 and 1. It's a horizontal compression towards the y-axis if b is larger than 1. And then if b is negative, it's done in a similar fashion like we did before, right? Okay. This is about, I think we made it through this one. Okay, let's just do more. So then using the graph of a function y equals f of x in a figure whose equation is not given, sketch each of the following graphs. So for A, we multiply the inside by a number between 0 and 1. For B, we multiply the inside by a number larger than 1. And for C, we multiply the inside by -2, right? So for A, for all of these are going to cause horizontal changes. For A, because the number is between 0 and 1, that should cause a horizontal stretch, so get wider horizontally. For B, that should cause a horizontal compression, so it should be smushed horizontally towards the y-axis. And then for C, we take the result from B and flip it horizontally over the y-axis. Okay, so we're going to have that here. So stretch horizontally by a factor of 2, so it's wider horizontally. Compress or shrink horizontally by a factor, well, by a half, but it's that same notion of reverses. Like before, where we said what value of x makes it 0. Now we're looking at what value of x makes it 1, right? So if we multiply the inside by a number larger than 1, you know, the y values basically are the x values are affected by 1 over that b, right? Okay, that's fine. But again, multiplying the inside by a number larger than 1 causes a horizontal compression. And then finally for C, if we multiply the inside by -2, it's going to flip it's going to be this graph, but flip horizontally over the y-axis. Okay. I'll just kind of mention this one. I think we got maybe 1 or 2 more after this, but this is probably the last one for the day. So if we wanted to sketch the graph of this equation, first thing is identify the basic function. So the basic function here, anybody see it? Y equals, so the basic function here is x squared. That's the main one that we're starting with. And again, when we do our transformations, multiple transformations in one equation, we work our way from the inside to the out. So the innermost transformation is going to be that -1. That's going to move it to the right by 1 unit. Okay. Working our way out. Now we multiply the outside by 2, which is larger than 1. So outside is going to cause a vertical. That's going to be a vertical stretch by a factor of 2. So stretch, I just abbreviate it, vertically by a factor of 2. After multiplying the outside by a number larger than 1, then we multiply the outside by a negative. So that's going to cause it to flip vertically over the x-axis. So we'll say flip over the x-axis. And then lastly, we added 3 on the outside. So that tells us to move up 3 units, okay? So this might take some practice to get used to. It's not obvious, but these are the concepts that come out in this course, right? Transformations of graphs. I wish I had actually gotten into this because like when I was a student, I started off in calculus, so I wasn't aware of this stuff. I knew how to graph this stuff. Like I knew how to like make a table, plot points, do certain things, but I never knew this stuff. And I wish I had known. It would have helped me on my journey. Like it totally would have helped. Maybe not you all because you're not necessarily, I don't expect you all to be mathematicians, but honestly, when I was a student, I wasn't planning on being a mathematician. I just had a knack for it. It made sense to me. So I just kept going with it as far as I could. And I'm still not done. I'll probably pick it back up at some point when I'm ready. But I'd rather go into law instead of get my PhD. I mean, at some point I probably will get my PhD, but I'd rather become a lawyer, get my money, get my billions of dollars. But anyway, but yeah, so a U-shaped curve, we go right 1 unit, stretch it vertically by 2, flip vertically over the x-axis, and then go up 3 units, okay? U-shaped graph, right by 1 unit, yeah, we got that. Stretch it vertically by a factor of 2, so the x values stay the same, but the y values are doubled. Flip it over the x-axis, and then go up by 3, okay? I think I'm gonna have to leave the rest as an exercise for you all, so I'm gonna leave this for you. Are there any burning questions?
So for the you said something about the bookstore for my math lab.
Okay, hang on. Yeah, give me a moment. Share, send it to box. Let me just make sure I'm in the right folder. Fall, traditional, this, notes, updated daily, right there. Okay, so when this bar finishes loading, you'll receive a copy of anything that you saw me writing. If you're trying to use the discount, you have to contact the bookstore. All right, they're the ones, because the email that we got, they were like, okay, we finally finalized the deal. And they were like, basically you had to enter this access code, but they were like, to get the access code, you have to contact the bookstore. So they're expecting you all just contact the bookstore, explain basically everything. And then, the deal is $100 for the access code, and they give you access to My Math Lab, full access to My Math Lab for 2 years. So for $100, full access to My Math Lab for 2 years. Okay. Any other burning questions? Going once, going twice.
So you go through the bookstore website?
I would just call them. I don't know if they have it online. I would just call during business hours and try to talk to somebody. Or
Okay.
either just go to the bookstore.
All right.
Okay. Any others? Going once, going twice. Forever hold your peas and rice. All right, gentlemen. So if there aren't any other burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy your evening. I'll see you all Wednesday, same time, same place. Take care, guys. Peace. Let's do this. Stop. Let me check the chat real quick. I mean, it's there, so I don't
I
know
had a
that.
quick question.
Yes.
Did you see my email I sent you the other day about me being away?
Was it for a marching band?
Yes, sir.
What's your last name?
Johnson.
What
What'd you say?
were the days?
It was last Wednesday through Sunday. I don't know what that date was. It should have been the 13th, probably the 17th.
What's your first name?
Jaden, Jaydhen.
You said last Wednesday?
And I sent one last night as well, or this morning as well. But I also sent one last Wednesday.
I'll just mark you as excused.
Okay, and then I know you said that 10% really doesn't hurt you that much, but is there a way that what's the face?
You talking about for
That
the
yeah.
I would just do those
All right.
just submit them and try to maximize your score.
All right.
Yeah, that's the best thing. You just get caught up and then
All right. Appreciate it.
try to be prompt going forward. Okay.
All right.
Let me see.
Appreciate it. Have a good one.
Mr. Grace, were you saying you have a similar thing as Mr. Johnson?
Yes, sir. I'm in the marching band as well. I sent you an email last week because I was absent last Wednesday because of the marching band.
Okay, I just marked you as excused.
Okay, thank you. I appreciate it, sir.
Hmm.
Have a good one.
Well, any others? Going once, going twice. Forever hold your peas and rice. Mr. Challenger, are you there? Can you hear me? All right. All right, gentlemen. Take care.